Hello and welcome back to this new video on Fourier series. So this is going to be a pretty long video and very intense integrations are going to be there. So please be patient while watching this video. In the description you will find the timestamp of the video so you can skip jump to the part which you think you want to see. Okay, so let's begin. So first of all, we are going to cover the graphical representation of Fourier series. Next, we will be establishing all the formulas required for solving a Fourier series, and then we'll solve a problem based on the mentioned formulas. Then I'll mention what is half range cosine and half range sine series, and we'll solve a corresponding problem to that. And finally, I'll discuss what is Parseval's identity, and we will be doing a problem based on Parseval's identity. So this is going to be the overview of today's video. Again, I'm repeating, it's going to be long. So if you want to skip jump to any of these, just find the timestamp in the description. Okay, so let's walk into the graphical representation of a Fourier series. So coming to the graphical demonstration, here you can see that I have a function which is in the blue color. Okay, so that's a function. Now I want to draw or plot a Fourier series of that function. The Fourier series is given by this sinusoidal looking curve. Okay, so now as I increase the value of n, as you know, a Fourier series consists of infinite series of combinations of sine and cosine series, a combination of them in an infinitely long chain. So as I increase that values of number of terms of the sine and cosine, which is represented by n, the Fourier series is going to start looking like this function. Okay, it's going to start replicate the function given to us. So as you can see, I am now going to increase the value of n, which is I will slowly slide the slider down to the right. So just keep an eye what is happening to this curve. As I increase the value of n, just see the function, the Fourier series is trying to replicate the original given function. Okay, so I keep on increasing the value of n and you can see what's happening to the picture, right? So the Fourier series is almost trying to represent the original function. Okay, so I'll just play it for you and you can see how if I decrease the value of n, how the Fourier series is becoming. And again, if I increase the value of n, as you can see the slider is moving, how the function is slowly and slowly trying to replicate our original function. Okay, so this is Fourier series and its graphical representation. Now I will move on to the problem solving formulas of Fourier series. So this is the formulas of Fourier series. It's saying that given a function fx and it be defined and integrable on an interval minus t to t, then the Fourier series of the function is given by something like this. Okay, a naught by 2 summation n equals to 1 to infinity a n cos n pi x by t plus b n sin n pi x by t. And where a0, the value of this a0 is given by this integration, the value of this an is given by this integration, and the value of bn is given by this integration. Okay, so this is the working formula for finding Fourier series of any given function fx, provided it is defined and integrable on the given interval minus t to t. Okay, so now we are going to use this formula and we are going to try to do this problem. Okay, so you can see it's given that we need to find Fourier series of the function x minus x square in the interval minus pi to pi. Okay, now observe carefully, when this t becomes minus pi to pi, okay, when minus t to t, when this essentially becomes minus pi to pi, then the formula becomes a little bit more easy to deal with. The pi in place of t, I am going to put pi now. So the pi in the numerator and denominator, they are going to cancel out. Similarly over here, in place of t, if I put pi, the pi in the numerator and denominator is going to get cancelled out. So this formula is going to look like a0 by 2 an cos, the pi will get cancelled, cos nx plus bn sin nx, provided when the interval becomes minus pi to pi. Okay, and similarly in place of this t, it's going to become pi, it's going to become pi, and it's going to become pi. Okay, and the pi will get cancelled here and the pi will get cancelled there. Okay, and the limits are going to become minus pi to pi, minus pi to pi, and minus pi to pi. So this will be the change in the formula if the interval becomes minus pi to pi. Okay. So now I'm going to try to find out the value of a0 first as per the given question. Okay. So we know that a0 is 1 by pi minus pi to pi fx dx. Okay. So now the integrations are going to be long. So if you want, you can skip jump to the final end result. Okay. So 1 by pi minus pi to pi, I have my fx function as x minus x square dx, and that would be x square by 2 minus x cube by 3 minus pi to pi. And or I could have done this in a little bit different way. I could have taken even functions and odd functions. Okay, so instead of doing it this way, it's more easier if you take the even function, odd function. So I will just quickly erase this off and break this up into two integrals, which is minus pi to pi x dx and 1 by pi integration minus pi to pi x square dx. Okay, so I've broken it up into two integrals. Now as you can see, this is an odd function. Okay, now what's an odd function? People who don't know what's an odd function, if f of x is equals to minus of fx, that's an odd function. Okay, and if f of sorry, I just wrote it wrong. F of minus x is equals to minus of fx, and if f of minus x is equals to fx, that means the minus sign is getting absorbed, then that's called an even function. Okay, so this is the definition of odd function and even function. Here you can see simply x, that means if I replace x by minus x, the minus is going to come outside, so this is an odd function. And for the second case, if in place of x I put minus x, then because of the whole square, it's going to get absorbed, the minus sign, so this is an even function. Okay, now using simple rules of integration, I can write this as integration of an odd function from minus a to a kind of limit, that becomes 0. Okay, and for the second one, I'll have 2 by pi integration 0 to pi x squared dx. Okay, now don't ask me how did that come, that's basic class 12 level integration. Okay, so minus 2 by pi x cube by 3 0 to pi, and that would become ultimately pi cube by 3 minus 0, right? So that becomes minus 2 pi square by 3. Okay, so that's the value of our a0. Okay, so now we're going to go and find out an and bn as per the given formulas. Now moving on to the an part, we know the formula for an is 1 by pi integration minus pi to pi fx cos the n pi x by t. In that formula, the t and pi was cancelling out, so as I told you, it was turning out to be nx dx, right? The formula which I had written just over here, cos nx plus bn sin nx, where an is fx cos nx dx, correct? So I have put that formula over here, and I'll write the function minus pi to pi. My function is x minus x square cos nx dx. Now again, the play of odd function and even function is going to arise, so I'll break it up into two integrals. So 1 by pi minus pi to pi x cos nx dx minus 1 by pi minus pi to pi x square cos nx dx. So again, you can identify this is going to be an odd function because minus sign gets absorbed inside a cos function, and this simple x is an odd function, so ultimately it becomes odd. Over here, both x square and cos x, they absorb the minus sign, so f of minus x would be equal to f of x, so that means this is entirely an even function. Okay, so that means the first integral is becoming 0, and for the second one, I'll have 2 by pi integration 0 to pi x square cos nx dx, right? So now I have to do this integration using the formula of by parts. Okay, so going into the by parts formula, so I'll be doing integration with respect to cos and differentiation with respect to x square. Okay, so it's going to be x square sine nx by n, that's the integration of the cos part. And the limit is 0 to pi, minus integration derivative of x square is going to be 2x, and integration of cos is going to be sine nx by n dx, and the limit is 0 to pi. Okay, so minus 2 by pi is there outside. If I'm going to put the limit, I know the value of sine n pi, that's going to be 0. And if I put the lower limit in the x part, that's again going to be 0. So this entire part is just 0. Okay, minus 2 by n. Again I have to do another by parts over here. So I'll just do that in the next step after a little bit simplification, so that I don't confuse up the minus signs and all the brackets. Okay, I want to get rid of so many brackets over here. So this would ultimately be 4 by n pi integration 0 to pi x sine nx dx. Okay, so now I'll go into the integration of this part, 4 by n pi. So the integration of sine would be minus of cos nx by n, and the limit would be 0 to pi, minus integration derivative of x would be 1, and integration of sine would be minus of, so I'm making it plus, minus of cos nx by n 0 to pi dx. Okay, so again I'll go into the integration part of this, 4 by n pi. If I'm putting the limits, then this is going to be cos n pi, so pi cos n pi, and if I put the lower limit 0, that's going to be directly 0. So I'll have minus pi cos n pi by n, the lower limit is becoming 0, so I'm not writing that, plus integration of cos nx, that's going to be sine nx by n. I already have another n from beforehand, so that's going to be n square, and the limit is 0 to pi. Okay, so 4 by n pi minus pi cos n pi by n, plus if I put the upper limit sine n pi, that's 0. If I put lower limit, sine 0 is again 0. So I have nothing to write over here, so the bracket closed. So I can see 1 pi is getting cancelled, and I'm having minus 4 cos n pi by n square. Okay, so that's the value of my an part. Moving on to the bn part. Now the formula for bn would be 1 by pi integration minus pi to pi. Instead of using the previous one where we had used fx cos nx, now I'm going to use fx sine nx for the bn part. So instead of the cos, now I'll have the sine part. Okay, that will be the main only difference. So I have fx sine nx dx. Okay, so that's going to be 1 by pi minus pi to pi. Fx value is x minus x square sine nx dx. Again, I'll split it up into two integrals so that I can define the odd ones and the even ones. So x sine nx dx minus 1 by pi minus pi to pi x square sine nx dx. Okay, now again it's time to identify whether we have an odd and even function over here. So we can see that x is an odd function and sin x is also an odd function. That means both of them are going to give out minus outside. What I'm trying to say is that f of minus x is going to be, one minus is going to come outside from the x part, one minus is going to come out from the sine part, and together is going to give back the original fx function. So when both are odd functions individually, the product becomes an even function, right? So this entire thing is an even function. But that's not the case in the next one, because sine is an odd function and x square is an even function. Now product of odd and even function is ultimately going to be an odd function. So only the sine part will give out the minus sign, and in the x square part the minus will get absorbed. So ultimately it's going to become odd function. So that means that integral is going to 0. So I'll have 2 by pi minus pi to pi, sorry, it's going to be 0 to pi x sine nx dx, and the other part is becoming 0. Okay, so I'll now go into the integration of this thing. 2 by pi x, I'm going to integrate the sine part and do the derivative for the x part. So I'll have minus x cos nx by n, limit being 0 to pi, minus integration 0 to pi x derivative would be 1 and sine derivative would be minus of, so making it plus cos nx by n, and I already have I think an so that's fine, dx. Okay, so now if I put the limits, you can see if I put the lower limit, that's going to be 0. If I put the upper limit, then that's non-zero. So I'll have 2 by pi. If I put the upper limit, I'll have minus pi cos n pi by n. The lower limit becomes 0, and integration of cos is sine, so I'll have plus sine nx by another n is going to get multiplied, so n square 0 to pi. Okay, so 2 by pi minus pi cos n pi by n plus, now if I put pi in place of x, sine pi is 0. If I put 0 in place of x, that's again 0. So I don't have a second part to this, and so the answer becomes a pi getting cancelled, minus 2 cos n pi by n. So that's the value of my bn part. Okay, so these are the three values that I've got, a0, an and bn. So I have got these three values. Now I'm going to use them and get my final answer. So as per the formula, we know that fx, the Fourier expansion, the Fourier series of fx is given by a0 by 2 summation n equals to 1 to infinity an cos nx plus bn sine nx. Right, we know this is the Fourier series, so I'm going to put the value of an, bn and a0 as per the things that I have found out over here. So that's going to be a0 by 2, so this 2 is going to get cancelled when I'm going to put it over there. So I'll have minus pi square by 3 plus summation n equals to 1 to infinity. The value of an is this thing that I've got over here, so that's minus 4 cos of n pi by n square cos of nx plus the value of bn, that is minus 2 cos n pi by n. So I'll just put that, I'll just put that right over here. So I'll put the value here, and I'll have the value of bn is, I'll need to erase the minus sign, plus sign, it will become minus 2 cos of n pi by n into sine nx, and that is the final Fourier series of the given function. Okay, so that's about our first problem, where we have solved or found out the Fourier series for a given function. Okay, so now let's go to the definitions of half range sine series, half range cosine series, and we are going to do problems based on that in the next few seconds. Okay, so let's quickly look into the formulas. Half range sine series. Now remember, whenever we are talking about half range, it's actually we are taking the interval 0 to t. Okay, instead of minus t to t, we were taking the interval minus t to t. So instead of that, now we are taking 0 to t, and we are assuming that in the other part of the interval, that means in the negative part of the interval from minus t to t, in this part we are considering that fx is given by, sorry, I will write it this way: f of minus x is given by fx. Okay, so we are just considering that when we are creating the half range sine or cosine series. Now what is the interpretation of half range sine series? That means we are constructing our Fourier series only with the sine part and not the cosine part. And when we are talking about half range cosine series, we are constructing our Fourier series only with the cosine part and not the sine part. Okay, and this is the respective formulas for half range sine and half range cosine. So in the half range sine, you only have the bn and the sine term, where bn is defined as follows. The only difference being you have a 2 in the numerator, which you did not have in the previous case, and you can see the limit is 0 to t. As I told you, we are working in this particular interval. Similarly, for half range cosine, the series is a0 by 2 summation an cos n pi x by t, where again a0 is given by another 2 is here, which was not there previously, and similarly in the an formula 2 is here, and for both the cases the limit is from 0 to t and not minus t to t. Okay, so this is about half range sine and cosine series. So this is the question given to us, that we have to find the sine series which represents the function fx equals to minus pi minus x in the given interval 0 to pi. So that means it's like the interval 0 to t, which I was talking about. Okay, so let's quickly start solving this one. As you know, since we are solving the half range sine series here, so that means the Fourier series would be summation n equals to 1 to infinity bn sine n pi x, and the pi n pi x by t, where the pi would cancel out. Since here t is same as pi, what I'm trying to say is it's going to be sine n pi x by t. Now since the value of t is nothing but pi, so t and pi will cancel, so I'll only have nx, right? And where my bn is given by 2 by t, in this case t is pi, so instead of writing t, I'll write pi integration 0 to t, which is pi in this case again, f of x sine nx. Correct? So that's the formula which is stated right over here for half range sine series, and I'm going to use that formula now to get the value of bn. Okay, so starting with the calculation of bn, I'll have 2 by pi integration 0 to pi. My fx value is pi minus x sine nx. So I missed the dx out here, dx. Okay, so I'll just do the integrations one by one, or I'll just separate out the integrals. 0 to pi pi sine nx dx minus 2 by pi 0 to pi x sine nx dx. Okay, so here the pi is getting cancelled. I'll have 2. Integration of sine is minus cos, so minus cos nx by n 0 to pi, minus here I need to do a by parts again, so minus 2 by pi integration of the sine part and derivative of the x part, so that would be minus x cos nx by n under the limit 0 to pi, minus integration derivative of x would be 1, so 1 0 to pi, integration of sine would be minus of cos, so making it plus cos nx, and n would be there, dx. Okay, so I'll just drag it down here, and now I'll just close the bracket. So I have, if I put pi and 0, so both the limits are going to exist, so I have minus 2 by n. If I put pi, it's going to be cos n pi, and if I put 0, that's going to be 1 minus 2 by pi. If I put pi, the limit is going to be there, but if I put 0, the x part is going to vanish, so I'll have minus pi cos n pi by pi. The lower limit is going to be 0, and if I complete this integration, I'll have sine nx by n square limit 0 to pi, and again sine pi is n pi is 0 and sine 0 is also 0. So minus 2 by n cos n pi minus 1, and minus minus it would become plus one of the I think this is supposed to be n and not pi. It's a writing mistake. It's going to be n. So this part is completely 0, so I'm not concerned about that. Pi is getting cancelled, minus minus is becoming plus, so I'll have 2 by n cos of n pi. Okay, so I can see something is going to get cancelled. Minus 2 by n cos n pi and plus 2 by n cos n pi, so that's going to cancel and I'll have only 2 by n. Okay, so that's the value of bn which I have got. Okay, and as per my Fourier series formula, which I written just over here, that's given by n equals to 1 to infinity bn sine nx, and I've got the value of bn just now, so I'll just put the value there. So I have the Fourier series is given by summation n equals to 1 to infinity bn sine nx, and I'll just put the value of bn out here, so it's going to be 2 by n sine nx. And if you want, you can just break the summation right over here. Well, that's not required actually, but still I'll just break the summation and I'll have 2, basically I can keep the 2 outside the summation, so 2 of sine, if I put n equals to 1, so I'll have sine x by 1. If I put n equals to 2, I'll have sine 2x by 2 plus sine 3x by 3, and so on infinitely. This is going to go on, and this is my half range sine series for the given function in the given interval. Okay, so we have done this problem. Now we'll move on to Parseval's identity. We'll discuss what that is, and from there we'll do a problem on Parseval's identity. Now talking about Parseval's identity, if the Fourier series of a function, if the function fx converges uniformly, okay, that's a requirement. If the function converges uniformly to fx, if the Fourier series of a function converges uniformly to fx in the interval minus t to t, then Parseval's identity is telling us that this thing, this integral 1 by t minus t to t, the whole square of the function, when that is integrated, that is going to be a0 square by 2 plus the sum of the squares of the Fourier series coefficients. Okay, the coefficient an, the coefficient bn that we find in Fourier series, the squares of that added together under the summation n equals to 1 to infinity, where, as I mentioned, a0, an and bn are nothing but the Fourier coefficients of fx. Okay, so this identity is called Parseval's identity, and this helps us get the values of several infinite sums. Okay, sum of infinite series, we can get the sum of that using Parseval's identity. Okay, so let's quickly look into a problem. So using Parseval's identity on the half range cosine series for the function fx equals to x in the interval 0 to 2, I need to determine what is the sum of this infinite series. Okay, so as I told you, using Parseval's identity, we find sum of infinite series. Okay, so the first objective is to find the half range of the cosine series. After that, we are going to use Parseval's. So first, let's focus on the half range cosine series for this given function. Okay, so as I have already told you, the half range cosine series formula is given by a0 by 2 plus summation n equals to 1 to infinity an cos nx dx, provided we use this formula when the limit was minus 0 to pi kind of a thing, right? But here you can observe it's not 0 to pi, it's 0 to 2, so I cannot write it this way. Okay, so I need to write n pi x by t, where my capital T is how much? My capital T is 2 in this case. Okay, so this is the t that we write in the formula, so I will have to write it as by 2, and here the pi is not going to get cancelled. Okay, and the formulas for a0 and an we have already told you before in this particular slide, right over here. The value of an is 2 by t 0 to t fx cos n pi x by t, and the value of a0 is 2 by pi 0 to t fx dx. Okay, so now I'm going to use these two formulas to find out a0 and an. Now I will start with a0. So as I have written the formula of a0, it's going to be 2 by capital T, which is 2 in this case, integration 0 to t, which is again 2 fx dx. Okay, so that's going to be integration 0 to 2. My fx is x dx, so x is square by 2, 0 to 2, so that's going to be 4 by 2 minus 0, so that's going to be 2 eventually. Okay, so got the value of a0, that turned out to be 2. Okay, so now go on to an. The formula for an is 2 by t again, so that means 2 by 2, 0 to 2. Okay, fx cos n pi x by t, which is 2 dx. Okay, so moving on with this integration, I'll have 0 to 2 x cos n pi x by 2 dx. So I'll have to do a by parts over here. So I'll integrate the cos part and differentiate the sine part. So integration of the cos part would be sine n pi x by 2 divided by the coefficient. So that would turn out to be 2 by n pi under the limit 0 to 2 minus integration. Derivative of x would be 1, and integration of the sine part, that would be having the same coefficient outside, and the integration of the cos would be sine n pi x by 2 dx under the limit 0 to 2. Alright, so I did not give any bracket there, so there's nothing to end. Carrying on with the integration, if I put 2 in place of x, then I'm going to have, so you can just observe, if I put 2 over here in place of this x, so this x and this 2 will get cancelled, so I'll basically have n pi, and the value of cos n pi is 0. And if I put the lower limit right over here, so that's also going to be 0, so the entire value of this is 0. So I'll now focus on the next integration. So now if I do that integration, I'll have another 2 by n pi minus of cos n pi x by 2, 0 to 2. Okay, so this minus and this minus together, they're going to become plus. So I'll have 4 by n square pi square. If I put the limits in place of 2, if I put x in place, 2 in place of x, that's going to be cos n pi. If I put 0, then cos 0, that's going to be 1. Okay, so that's the value of an that we have got. Okay, so I'll now put these values in the half range cosine series. So my Fourier series is going to become a0 by 2 plus summation n equals to 1 to infinity an cos n pi x by 2. Okay, so if I put that, I'm going to have the value of a0 was how much? The value of a0 was 2. So I'll have over here 2 by 2 plus summation n equals to 1 to infinity. The value of an is what I've got over here, 4 by n square pi square cos n pi minus 1 whole into cos of n pi x by 2. Okay, so this is, so if I just cancel out the 2 over here, that's going to be 1. So I'm not going to write 2 by 2. So eventually that's going to be 1. And this is my half range cosine series for the given function. Now moving on to the Parseval's identity part. Now only for doing the Parseval's part, I did not need to find the Fourier series, half-range Fourier, explicitly writing it was not required. Only finding the an part would have been enough, but I just did this so that if you got the question that find the half-range cosine, then this would have been your answer. Okay, but if your objective is only to determine the infinite sum of the series given in the question, then this part is not required to write, which I have written in the green color. So I can directly move on to the Parseval's identity. Okay, so using Parseval's identity, the formula which I just mentioned was 1 by t, that's 1 by 2, minus t to t, so that's minus 2 to 2 as per the formula I'm writing it. So f of x whole square dx, this was equals to summation, before that I had a0 square by 2 plus summation n equals to 1 to infinity an square plus bn square, right? This was my Parseval's identity. As per this question, in place of t I have written 2. Okay, now see, we are doing Parseval's identity for half range cosine series. For half range cosine, you have the value of an, you don't have any bn value, okay, because this is half range cosine. So that means this part is 0 when you are using Parseval's on the half range cosine part. Similarly, if you were using Parseval's on the half range sine part, your an part would have been 0 and your a0 would also have been 0. You would only have the bn part in that case. Okay, and if you are using Parseval's on a general Fourier series, not half range cosine or half range sine, then this is the general formula that I have stated right now. Okay, so I'll just put the value of an that I have got, and I'll do the LHS also. So that's half of minus 2 to 2. My function fx was given as x in the question, so it's going to be x square dx equals a0 square by 2. Now what's the value of a0? A0 value was 2, I had found that before, so it's going to be 2 square by 2 plus summation n equals to 1 to infinity, only the an part, and the an part I have found out to be this particular value, 4 by n square pi square cos n pi minus 1. So I'll just put that, and it's going to become 16. So the square of 4 would become, I'm just squaring this part, right? This is the an part, as you can see, this is the an part. So basically a whole square of this part is what I need. So it's going to be 16 by n to the power 4 pi to the power 4 and a whole square of this part, so that's going to be cos n pi minus 1 whole square, and the bn part is 0. Okay, so I just need to simplify this and get my required answer. Okay, so half, now you can see this is an even function. Okay, x squared is an even function. I have minus 2 to 2, so it's going to be 2 times 0 to 2 x squared dx as per even function formula equals 4 by 2, that's 2, plus summation n equals to 1 to infinity 16 by n to the power 4 pi to the power 4. So we know the value of cos n pi, that is minus 1 to the power n minus 1 whole square. Okay, so I'll further do the integration on the left hand side, and I'll have, it's the value is x cubed by 3 0 to 2 plus, actually I can bring the 16 and pi by 4 outside the summation, that's a constant. So 16 by pi to the power 4 n equals to 1 to infinity, and I have minus 1 to the power n minus 1 whole square by n to the power 4. Okay, so if I put the value, it's going to be 8 by 3. I can bring the 2 this side, so it's going to be minus 2 equals 16 by pi to the power 4. Now I'm breaking the summation one by one. Okay, if I take n equals to 1, okay, if I take n equals to 1, then minus 1 to the power 1, that would be simply minus 1, right? So this is minus 1, I have another minus 1, so together that's going to be minus 2 whole square, that's going to be 4. Okay, so 4, and I have taken the value of n to be 1 in this case. All right, plus Now I'm taking the value of n to be 2. Okay, so if I take the value of n to be 2, so minus 1 square, that would be 1. So you can see the numerators are becoming 0. Okay, plus 1 minus 1, that's 0. So I'm not getting any term when n is 2. If I go on to n equals 3, then minus 1 to the power 3, that's again going to be minus 1. So in the numerator I'll have minus 2, just like before. So minus 2 whole square, that's going to be 4, just like before. So plus 4 by, I have taken the value of n to be 3, so I have 3 to the power 4. Similarly, you can see whenever I am taking odd, so even power, it's becoming 0 in the numerator. So if I take n equals 4, that's an even power, so the value is going to become 0. Next, if I take an odd power 5, then again numerator is going to be same as before, which is going to be 4 by, I have taken n value to be 5, so 5 to the power 4, and this pattern goes on. So you can understand what is the pattern on the RHS part. So I'll just simplify this a little bit more. On this side I'll have 2 by 3 equals 16 by pi to the power 4. You can see I can take a 4 common from the entire numerator part. I have 4 in each of the terms. So a 4 is taken out common, and I have 1 by 1 to the power 4, 1 by 3 to the power 4, 1 by 5 to the power 4, and so on. So I can just cross multiply the terms on this side. Before I cross multiply, I can cancel out the 2 with the 4, and I'll have 2 remaining. So I'll have 32 that side. So I can bring the pi by 4 this side, and I have 3 and a 32. So that's 96. And on the RHS, I'll have 1 by 1 to the power 4, 1 by 2 to the power 4, 1 by 5 to the power 4, plus dot dot dot. So we have got the sum of all the power force on the right hand side in the reciprocal format, but you can see it's not matching with the question right now. Okay, if you look at the question, you will see that in the question I had the series where the sum consists of all the terms, 1 to the power 4, 2 to the power 4, 3 to the power 4, 4 to the power 4, like this, all the terms are there. But what I have found out using Parseval's identity, I only have the powers in the odd terms, the even terms are not there. So that means this is not my final answer yet. I need a little bit more manipulation. Okay, so just see, it's going to be a very small manipulation that I'm going to do. Let's say I'm calling this value to be S. Okay, I'm calling this sum to be S, and the value of S I have got is pi by 4, pi to the power 4 divided by 96. Okay, for now, just forget the value. Let's say I'm calling the thing to be S. Okay. Achha. So let me do one thing. Let me call it S1. Okay. Let me just rename it. Let's call it S1. I need to find out S, where S is 1 to the power 4, 2 to the power 4, 3 to the power 4, 4 to the power 4. Like this, it goes on. Okay. Now you can observe that I can selectively take the odd terms here. Okay, I am selectively taking the odd terms. That means the first one, the third one, then I'm taking the fifth one, and so on. I'm clubbing them and making them a group. And I am taking the remaining even terms. The even terms are 1 by 2 to the power 4 plus 1 by 4 to the power 4 plus so on. Okay. And the total summation, I'm calling it S, which is my target. Okay, the value which I actually want to find out. Achha. Now this part is the S1 part, which I told you right now. So that's the S1 part. And from here, imagine I'm taking a 2 to the power 4 common from the denominator. Okay, I'm taking a 2 to the power 4 common from denominator. So what will I have? I will have 1 by 1 to the power 4. That means simply 1. If I take 2 to the power 4 common from 4 to the power 4, now think carefully, don't make a mistake here. From 4 to the power 4, I can write 4 to the power 4 as 2 to the power 8. So if I take 2 to the power 4 common from that, the remaining thing will be again another 2 to the power 4. Okay, so don't make any confusion here. From 4 to the power 4, if I take 2 to the power 4 common, what remains is again another 2 to the power 4. So that means if I have taken 2 to the power 4 common from here, what is remaining is 2 to the power 4. Similarly, the next term here is actually 1 by 6 to the power 4. and from 6 to the power 4, if I take 2 to the power 4 common, so again observe, I can write this as 2 to the power 4 into 3 to the power 4, right? Basically it's 6 to the power 4. So from here, if I take 2 to the power 4 common, what remains is 3 to the power 4. Okay, so from this term, if I take 2 to the power 4 common, I have 3 to the power 4. Okay, plus dot dot dot. So you can see I am again getting back my original capital S series. That means the original series, I am again getting it back right over here. So over here I can substitute S. Okay, so S equals S1 plus S by 2 to the power 4. Okay, so I'll take both the S on the LHS part, and if I take the S common, I'll have 1 minus 1 by 2 to the power 4 equals S1. Now S1 is what the value which I had found out before. I had named S1 pi to the power 4 by 96. So I'll just put that. So I have S1 as pi to the power 4 by 96. So over here, if I simplify, it's 16 minus 1, that's 15 by 16 equals pi to the power 4 by 96. So that means S would be 16 into pi to the power 4 by 15 into 96. And if you just simplify that a little bit, it's going to end up at pi to the power 4 by 90. Okay, and that's the required answer. Okay, S was the required sum of the series that we were trying to find out. Okay, so I hope this video helps. This video is completely oriented to solving the problems of Fourier's and not concentrating on the major concepts. So if it helps, please share the video with your friends. Thank you. Have a nice day.